Hello everyone, in this video we're going to be talking about the SN1 reactions and their important points. So to start out with, let's talk about a generic SN1 reaction or SN1 step. So SN1 reaction is going to be happening in two steps where I can have an alkyl halide. So this is going to be our alkyl halide. I'm going to make a secondary alkyl halide here. So suppose I got an X as my leaving group. So that could be either chlorine, bromine, or iodine. So in the first step, you have this leaving group leaving. So you can kind of see the difference between what happens in SN2 and SN1. Um, in SN2, you're going to have the nucleophile attacking and the leaving group leaving at the same time. But in SN1 reactions, your leaving group would leave first. And when the leaving group leaves, you're going to be making a carbocation. And obviously, there is going to be an halogen close by. So still your charges are conserved there. So that's going to be, this particular step is going to be the formation of carbocation. And usually the formation of carbocation, which is going to be the first step, usually the first step, unless you're dealing with an alcohol, then you may have to protonate him before you can make a good leaving group. But when we're talking about alkyl halides, it's going to be loss of leaving group, making it a carbocation, and then in the second step, I can have the carbocation that you have just made. That's going to be attacked by your nucleophile. So it's going to be, so let's say I got this nucleophile, suppose here. So this nucleophile is going to be attacking this carbocation to make your final product here. And I'll talk about the stereochemistry later on, but now I just want to talk about just the general step there. So this is going to be your final product. So this is going to be your second step. Second step is going to be the fast step, and your first step, which is this formation of carbocation, is going to be the slow step, which we can also say is going to be your rate determining step. So at the end of the day, you got two steps being involved here. You got an alkyl halide, so you got to put it right here, which is going to be your substrate. And then I got a nucleophile, which is going to be right here. And then obviously your leaving group here, we have said it's going to be some sort of halogen, which is the chlorine, chloride, bromide, or iodide for the most cases when we're talking about these SN1 reactions. And obviously they're not only limited to those, you can also have alcohols and some other good leaving groups. But here we would focus on your your alkyl halides only. So now the question is why it's going to be called SN1 reaction. So far what we said, we have two steps where the first step, which is going to be your formation of carbocation, that's going to be your slow step. And in that slow step, you only have one reactant in there, or another way of saying you only got the alkyl halide that's going to be taking part in that particular rate determining step. So obviously, the S stands for the substitution, N stands for the nucleophilic, and then your SN1 reactions, they are going to be the unimolecular. They're not going to be bimolecular. So I'm going to change that here. And the unimolecular comes from one here. And the reason why they are unimolecular, because I have only one type of alkyl halide or one reactant that's taking it apart when the rate determining step, which is going to be your alkyl halide. So when it comes down to writing the rate of this reaction in terms of kinetics, I'm going to be doing rate equals rate constant K. And now I'm going to be going back and looking at my rate determining step, which is the formation of carbocation. And I only got the alkyl halide in there. So I'm going to go ahead and writing that in the form of Rx there. So R means alkyl and X means the halide. So that's just a generic way of writing this alkyl halide here. So overall, your SN1 reactions are going to be first order as opposed to SN2 reactions where second order because the SN2 reaction also depended on the nucleophile. Now, these guys only depended on your alkyl halide. They're not really going to be dependent on the nucleophile. So you can get away with a weak nucleophile in these particular reactions, but that doesn't necessarily mean if you have a relatively stronger nucleophile, you cannot have an SN1 reaction. you could still have an SN1 reaction if you have a little bit of stronger nucleophile as well. So we're going to be looking into those factors later on as well. But overall, the nucleophile does not play a role in determining the rate of these SN1 reactions. Okay, let's talk about the stereochemistry now. So if I go back and probably just pick the same um, type of reaction here, so suppose I got this secondary alkyl halide here, and suppose I got this chlorine that's kind of coming out of the page. So the first step here is going to be the loss of leaving group. So this leaving group is going to leave, and I'm going to be making a carbocation that's going to look like this. Okay, and then that's going to be your first step, which is the rate determining step. Your second step is going to be the attack of nucleophiles. But before we go anywhere, I want to be focusing some time, we're going to spend some time on this carbocation. Now, this particular carbocation is going to be in a secondary carbocation, and then it's also going to be chiral at the end of the day, or another way of saying when I'm looking at my molecule in the beginning, this carbon center was chiral, and when you make this carbocation, now this carbon is going to be all of a sudden sp2 hybrid. So that carbon right there is going to be sp2 hybrid, which means it's going to be having a geometry of trigonal planar. So it's a planar geometry. So when I have the nucleophile attacking that particular carbon, it could attack from the top or it could attack from the bottom. So let me just go ahead and copy this down here. So I could have a nucleophile, and I can take any generic example of nucleophile. Suppose I'm getting a weak nucleophile or something like water, suppose. I got this water, and then this water either could attack from the top, something like this, or it has the possibility of attacking from the bottom. So either one of those um, attacks are going to be having a 50-50 shot. So when you do attack from the top, suppose, then how my product's going to look like? Well, it's going to be coming out of the page, and that's going to be looking like this. There's oxygen now attached to that carbon, so that's going to be coming out of the page because it's attacking from the top. And then this oxygen is still going to have the hydrogens attached. Now, remember, the oxygen used one of its lone pairs to make a new bond with the carbon, so it's still going to have one lone pair left, but then all of a sudden it's going to have a positive charge, positive formal charge, because now it has three bonds. So that's with when it's attacking from the top. But when it does in a bottom attack, how's that going to look like? Well, everything else is going to be the same except your new bond is going to be going back into the page there, something like this. So you have a 50-50 shot of these nucleophile attacking this carbocation either from the top or from the bottom, and as a result, you're going to be getting a racemic mixture. So anytime you get a 50% S, 50% R, you're going to be getting in racemic mixtures. Now keep in mind, you may not get a racemic mixture if you have another chiral center already present in the molecule and you're not messing up with that particular chiral center. If you have only one chiral center and when you do make your products, you're going to be getting a 50-50 of those two, and you're going to be getting your racemic mixtures. Obviously, your reaction is not complete. We said typically these SN1 does takes place in two steps, like we have here, but sometimes you may have a third step, which is literally going to be an acid-base reaction because this is not neutral yet. So what I'm going to be doing here, I'll just do only one of those basically. I'll take this one and I'm going to be running a acid-base reaction on it so that we can have a neutral alcohol here. Now, mechanistically, you can have this chloride that you have left in the beginning, um, grabbing this proton. So this is just a typical acid-base reaction now. And then this is going to go back and restore the electron density back on to back onto the oxygen there. So maybe I can just again duplicate that and then just take this one out. And then I got two lone pairs on the oxygen now. So that's how it's going to look like. And obviously, you're also going to have your other product, which is going to be your enantiomer. So you're going to have a two lone pairs here. So this is going to be your third step, and that would happen sometimes when after doing the second step, your products are not neutral. So you would do a acid-base reaction to get into the third step. Now you get a 50% R, 50% S here. So this particular group, this is going to be 1, 2, 3. So that's going to be R. And when I look at the second one, 1, 2, 3, it's going clockwise, but then you would have to flip it because your uh, lowest priority group, which is hydrogen, would be coming out of the page here. So this is coming out of the page, so you're going to have to flip it. So when you flip it, it's going to be an S. So you get 50% R, 50% S. That's going to be called in the racemic mixtures. Racemic mixtures are made only when you have half of 50% R and 50% S. And even though you have chirality in the racemic mixtures, because both of those compounds are chirals, and they are capable of rotating the light one way, but these racemic mixtures, they will be achiral because one compound will rotate the light one way and the other compound will rotate the light the other way. So this is how the mechanism is gonna look like. And at the end of the day, the stereochemistry tells you you're gonna be making racemic mixtures unless you have another chiral center in there. Then in that case, you would be making diastereomers. And in a separate session, I'll talk about some of these examples. Okay, and then if I want to compare that momentarily to the SN2 reaction, remember SN2 reactions were taking place only in one step, and it had a backside attack involved. And when it had a backside attack involved, it would be making a inversion in stereochemistry, or if you started out with an S, you made the R and vice versa. But here, it doesn't really matter whether you start out with an S configuration or R configuration on the reactant side. At the end of the product, or at the end of the day, your products are going to be the racemic mixtures in this particular case. So this is what the mechanism going to be and the stereochemistry going to look like. Now let's talk about how do you know when a particular reaction is going to be an SN1 reaction, just like we have talked about in case of SN2 reaction? Well, the question you want to ask yourself in case of SN1 reactions, under what condition or which particular alkyl halide is going to be making the most stable carbocation? Because remember, these mechanisms undergo through the formation of these carbocation. So you want to make sure you're making a stable carbocation. If you're not making a stable carbocation, you're not going to be able to do the SN1 mechanism. And in terms of secondaries and tertiaries and primaries in metal, we know your tertiary carbocations are going to be the most stable. So let's talk about the stability. So this is going to be the most stable, and then followed by your secondaries are going to be a little bit less stable, and then your primaries are very less stable, and then your metals are even less stable carbocations than the other ones. So the bottom line is, if I have a secondary and a tertiary carbocation, I should be okay. So you can make the secondary carbocation and you can also make a tertiary carbocation, but you cannot make a primary and the methyl carbocation. So they are not going to be stable. So when I'm looking at the type of alkyl halide, I can say, okay, I'm going to be having a tertiary alkyl halide followed by the secondary alkyl halide, and then your primaries and your methyls don't really do SN1 mechanism. So this right there, they're not, no, I'll just write down no SN1 mechanism on those. But when we're looking at the tertiaries, they are going to be the most likely to do the SN1 mechanism, and their secondaries are going to be a little bit less likely to do the SN1 mechanism. but then your primaries and methyls will not be doing the SN1 mechanism. So this is going to be so if you recall what happens in case of SN2, SN2 were actually opposite. You want to have a methyl and primaries doing the SN2, and you could also have the secondaries doing the SN2, but you were not able to have tertiary alkyl halides doing the SN2 mechanisms. Let's talk about now nucleophile. Like so far, what we have seen that the secondaries is the common point. If you have a tertiary alkyl halide, you know it's got to go SN1. If you have a primary or a methyl alkyl halide, you know it's got to go SN2. But if it's a secondary, that's when sometimes you got to look at some other factors, and especially, what the nature of nucleophile is, what the nature of solvent is. Those are the main important things. Now, as far as your SN1 reaction go, the question is, was the nucleophile in the rate determining step, or did you write the nucleophile in the rate law expression? And the answer is no. Well, you did not have the nucleophile in the rate determining step, so it's okay to have a weaker nucleophile for these SN1 reaction. So some of the examples of weaker nucleophile is going to be like H2O, CH3OH, some of these neutral compounds, OH. And then you can also, then the question comes in, can you have a stronger nucleophile and have an SN1 reaction? And the answer is yes. You could literally have an SN1 reaction even with a relatively stronger nucleophile, as long as you have a tertiary alkyl halide. Because the tertiary alkyl halide is not going to be doing an SN2 reaction. It's going to be only doing the SN1 reaction. You just have to be a little bit careful with what nucleophile you're picking. You cannot have a strong base though. If you have a strong base and a strong nucleophile, then it's rather going to be doing an elimination reaction. So I could still have like SH minus, and then I could still have, CN minus, and I can still have something like acetate. In terms of their basicity, some of those bases are a little bit stronger than the other ones, but they're not very strong bases. So they are just in the general ideas of they would be acting rather as a nucleophile than the base. And then you have some borderline nucleophiles, like I can have H2S, I can have NH3, or I can have any amine basically. So these guys, they're not really super strong nucleophiles. They're not really weak nucleophiles. They are like on the borderline. So they can still do a SN1 reaction. But the take-home message here you want to have for SN1 mechanisms, you can have a weak nucleophile, but if you have a stronger nucleophile and if you're dealing with a tertiary alkyl halide, you can still do an SN1 reaction with those. The order is always going to be figure out what type of alkyl halide you have, and if you can, just based on the alkyl halide, if you can figure out whether it's going to be an SN1 or SN2, then you don't have to worry about looking at your nucleophile. But if you can't figure out, especially if you have a secondary alkyl halide, then that's when you got to look at your nucleophiles. Then in terms of your solvent, sometimes solvents can also help you. Obviously, you do need polar solvents, but even among polar solvents, the SN1 are preferred with polar protic solvents. So remember, your SN2 were preferred with polar aprotic solvents, and your SN1 is going to be preferred with polar protic solvents. So some of the examples of polar protic solvents are like water, any sort of alcohol like methanol, or I can talk about ethanol, or I can even talk about acetate or acetic acid or ammonia. These are the most common polar protic solvents you're going to be looking into. And obviously your polar aprotic solvents are like acetone, and you got DMSO, and then you have DMF, ether, and then you can also talk about acetonitrile. So those are your polar aprotic solvents. Remember, the difference is polar aprotic solvents is going to have an oxygen hydrogen or oxygen nitrogen or an oxygen fluorine bond, which is going to be capable of making hydrogen bonding. But you're not going to have such a bond in polar aprotic solvents, and they're not going to be able to make hydrogen bonds among themselves. Let's talk about the possibilities of carbocation rearrangement. Now, you don't really see that in case of SN2 reaction, because SN2 reactions don't do any carbocation, don't make any carbocations, and they're not going to be doing any carbocation rearrangements. Now, whenever you do go SN1 reaction, like in this particular case, this is going to be my secondary alkyl halide. Now, secondary alkyl halides could go SN1 and SN2, but when I look at my nucleophile, I got water, which we know it's going to be a weak nucleophile. And since it's a weak nucleophile, it's got to be going an SN1 mechanism. So when I'm doing the SN1 mechanism, the first step is obviously going to be the loss of leaving group. So when this leaving group leaves, so this is how it's going to look like. You're going to have a positive charge here and the chloride here. Now, anytime you make a carbocation, figure out what kind of carbocation you have made. So in this particular case, I have made a secondary carbocation. Okay, and if you are making a secondary carbocation, always be on the look if you can somehow make a tertiary carbocation by doing a adjacent rearrangement, adjacent methyl or hydride shift. If I'm looking at my adjacent positions, like this one right there, especially on the left, if I can move this positive charge onto the left side, it's going to be making a tertiary carbocation and it's going to be more stable. So that's going to be your carbocation rearrangement. Now, what I see on this left carbon, that I got two methyl groups, and your third group is going to be obviously the hydrogen. So I'm going to be doing a so-called hydride shift here. So let me just take that here, copy this down here. So I can do so-called a 1,2 hydride shift. When you're drawing the mechanism of the hydride shift, you're going to be taking that bond or the electrons that's in the bond onto that new location of this positive charge. So make sure you draw something like this from the bond onto that positive charge. So when you do make your product now, so your obviously your hydrogen is going to be moved down here, and this carbon is going to be the one that's going to be having the positive charge now. So all of a sudden, this is going to be your tertiary carbocation. And always keep in mind, they may not even write that hydrogen there. There's a good chance they will probably just write this particular compound um, just like this with a positive charge. And sometimes the students wondered like where that hydrogen go. Well, because remember, you don't really have to show the hydrogens in the skeleton structure that are on the carbon, so that's why it's not going to be shown there. So this is going to be your carbocation rearrangement, and then after that, you can have the nucleophile attacking here and making the final product. So this particular one is going to be your tertiary carbocation. That's one type of carbocation rearrangement you can see. The other type, you can also have so-called a methyl shift. Now, in this next example, I still got the secondary alkyl halide, still got water, which is going to be a weak nucleophile. So what that means, I can have this kind of gone. If I lose this one, I'm going to be making a positive charge here, and obviously the chloride right here. So now this is again a secondary carbocation, and if I can somehow move this positive charge onto this next location, I would be able to create a tertiary carbocation. But in order to do so, I already have methyl groups onto that left carbon, so I would actually have to move out. Copy that down. I'm going to have to migrate your methyl in this particular case. So I'm going to be saying, okay, it's rather going to be a methyl shift. It's going to be 1,2 methyl shift. Now keep in mind, for the most part, you're only going to be shifting from your adjacent positions. You're not going to be shifting from your um, like third or fourth carbons. It's only going to be the adjacent carbon, unless you're doing something like a ring opening that I'll talk about in a little bit. The ring openings is a little bit of different or special type of carbocation rearrangement, but when you're just going from an open chain, you're only going to be moving one carbon away, either to the left side or to the right side, depending on which side makes the most stable carbocation. And if you don't have a possibility of making the stable carbocation, you don't really do any carbocation rearrangement in that case. So this methyl, I'm gonna draw this a little bit carefully here. So those were two, and then this metal comes down here now, so that's going to be the positive charge. So this has made a tertiary carbocation now, which is going to be more stable. And then your water can come in and do the attack, a nucleophilic attack there to make the final product. So I'm not really going to draw that. I'm just going to be focusing on the carbocation rearrangement here. Now this next one is a ring opening type. So similarly, I got the secondary alkyl halide, got a weak nucleophile. So the first step is going to be leaving uh, a leaving group would be going away. So when this leaving group leaves, so let's see what kind of carbocation is going to be made here. It's got a positive charge here, and then you're going to have this Cl minus right there. Now, obviously, I got the secondary alkyl halide, and someone might think, okay, I'm gonna be making this positive charge move to the left carbon here by doing maybe a methyl shift so that I can have a tertiary carbocation. That's a okay thinking, but the other thing you have to think of here, there's a lot of ring strain in this particular cyclobutyl group. Your cyclobutyl, cyclopropyl, those rings are not very stable because of the angle strain there. Their angles, like in this particular case, is a 90 degrees in the ring, and that's going to be obviously away from your ideal tetrahedral angle, which is supposed to be 109 degrees. So since it's away from the ideal angle, there's a lot of ring strain, there's a lot of instability. So instead of moving that metal, there is going to be a ring opening. So if I want to go ahead, let me just do that. It's on the next page. If I go ahead and call this 1, 2, 3, 4, and 5, what's going to happen? It's going to have a ring opening where this carbon 5 is going to be the one that's going to be moving down here. So carbon 5 is going to be connecting with carbon 1. So then all of a sudden you're going to have 5 carbon ring now. So I'm going to go ahead and draw 5 carbon ring here. And I'll go ahead and number those just like we have seen. So I got 1. So you know 1 is still going to be connected to 2 here. And then you get 3, 4. And then also 1 is going to be connected to the 5 all of a sudden. And this 1 is also going to having this methyl group attached to it to make sure you don't forget about that. And then this 1, this second carbon also have another methyl group attached right there. So then got to make sure you draw the methyl group there. Now, where does your positive charge go? That's another thing you got to be careful with. Now, keep in mind that the bond that you're actually breaking is the one between the second carbon and the fifth carbon. So since you're breaking that bond and this fifth carbon is making a new bond with that carbocation, your second carbon becomes electron deficient. And since your second carbon becomes electron deficient, second carbon is the one that's going to be getting the positive charge. So that's where your new carbocation going to be. So this is going to be a ring expansion. And then similarly, you can have a ring contraction as well if you don't have a stable ring. So ring expansion will take place if you have, something like a 4 carbon ring or maybe a 3 carbon ring, because those rings are not stable. Your stable ring is going to be the 5-membered and the 6-membered ring. But if you have a 7-membered ring or an 8-membered ring, then you can have a ring contraction where you're actually going to be closing up the ring to bring a 7-membered ring down to 6-membered ring, something like that. So this is how you're going to be looking at your carbocation rearrangements. Make sure you always be on the lookout whenever you make the carbocation if you indeed have a stable or not a stable carbocation. Finally, I'll talk about the energy profile diagram. So when we talk about energy profile diagram, I mean, so far we have seen you're going to have at least 2 steps in the mechanism, but then you can also have 3 steps in the mechanism depending on if you do have an acid-base reaction. But the most important part is going to be your first step, which is the formation of carbocation. That's going to be your most energy consuming step or the slowest step, and that's going to be your rate determining step. So if I'm doing generally doing this in two steps, for example, then obviously I'll go ahead and do the first step. Okay, so this first step is going to be making this intermediate here where you're going to have a carbocation, and obviously it's going to be making in a transition state 1. And then in the next step, this carbocation is going to be turning into your product. And this is going to be obviously your reactant here. Now you can clearly see that we have made this energy for the first step to be a lot higher because that is going to be your rate determining step. So this is going to be the activation energy for step 1, and this is going to be your activation energy for step 2. So clearly the EA1 is going to be bigger than EA2. Now, in some cases, it may slightly look different because when you're talking about nickel alcohols don't really have a good leaving group. And if you're trying to do like SN1 mechanism or even like E1 mechanisms on alcohols, you would have to protonate the alcohol. So you will have another initial step before this uh, carbocation formation step in that particular case. So this is just like a general representation of an SN1 reaction where most likely they're going to be doing it in two steps, but that doesn't necessarily mean they will be doing only two steps always. They may have, a third step where you're going to have this acid-base reaction like we have done in the example. So then you will have another energy hump, smaller energy hump before you make the product. However many numbers of steps you're going to have, that's how many energy humps you're going to have in there. So this is going to be having the second transition state here. So number of steps is going to be equal to the transition states. Your carbocation or your intermediate is always going to be one less than the number of steps. In this case, you have two steps. I'm going to be making one intermediate in this case, and that will happen to be the carbocation for our case. So this is the overall representation of these SN1 mechanisms. And like I said, the most important thing is your stereochemistry. What really determines whether it's going to be an SN1 is going to be the type of alkyl halide. If that can't determine, then you look for the nucleophile and the solvent usually together. And same can be said about the SN2 reaction, because if you have a primary or methyl, then it's clearly SN2. But if you have a tertiary, then it's clearly SN1. The problem comes in whenever you have a secondary. So secondaries could be going any of those two mechanisms, and that's when you most likely going to be focusing on the nature of the nucleophile and the type of solvent you're using in there. All right, so if you have any questions on any of this, feel free to leave any comments in the section below.